Well, thank you for coming back to our third seminar this week, which is going to be given by Marie Pushkova, and she's going to be talking about robust monitoring of CAPM portfolio betas.
Thank you for the introduction, and thank you very much also for invitation to participate in this event. It's really wonderful. I am enjoying it so far. So I am giving the talk according to the title. It's robust monitoring. Monitoring means sequential CAPM model, so that means that it is connected with econometrics. But I am more from statistical side, so I will try to explain you. Well, so, okay. So just what I am going to present are papers written with three co-authors, Chochola, Prashkova, and Steinebach. One of them appeared last year in Journal of Multivariate Analysis. The other one was just submitted, I think, during the last week. And what is said behind it, this is a change point problem, one thing. It's the so-called online versions that we have one observation arriving after another, so that sometimes it's called monitoring also. This will concern because we have this CAPM model. These are the particle regression models behind it. The data will be mostly multivariate, but I will, in the last part, mention also the functional data, so that's the case when we have or high dimensional data. Then generally the observation will be assumed dependent. And here is a misprint. There is LPM approximability or strong mixing. I will stay with the first notion, and all results will hold true even for strong mixing. And then the robust procedure, I mean that will be somehow so-called M procedures. So this is behind it. Okay, and I will try to. So at first, what I mean by the CAPM or capital assets pricing model? It's formulated. Here is the basic equation. If you go to the literature on this topics, you find a number of various observations. But I choose for the beginning this type of models that beta j are unknown parameters. We have j is going from 1 up to this, so that means that we have a multivariate situation. But what is here said, this RTJ is a return of an asset at time t. We have the RTM, which is a return of the market portfolio at time t. And here we have the riskless security, and this is something, some excess return or premium risk. And what is of the interest are these beta j. So this is why there was in the title this portfolio betas. Okay, so this is the model. So but we will reformulate it slightly more in a statistical way, that we assume that in fact we have a model where this return of the j's asset at time t can be expressed like this. This is this is the error term. The beta j's are the parameters of interest. Alpha j are not of the parameter of interest. So this is what we have, and so because I said that we are working in the area of the change point problems, that we assume that both parameters alpha and beta also depend generally on the time t, and this is general model set. And I spoke about the online monitoring on online procedures. This is we will assume the following setup. We assume that we have a historical or stable or training data of size m, where we assume that the parameters are staying constant, they don't change with the time. And then we start, after having this historical data, we start with monitoring new data, and the question is whether we have the situation that the parameters beta are staying constant over the whole observational period or forever, or whether there is a change at some point k star. That is so far, so that the alphas are not included. Of course, this k star is it depends generally on m, and we call it this is a change point problem. So we have this thing, and said the issue is to construct the test procedure for such a situation. This is typically is of the form that we have there the product on the left hand side. We have so that this is a ratio. Q hat is a statistic based on the m plus k observations. So this is when we have m plus k observations. This Q is a kind of boundary function that somehow gives the standardization with respect to t, and then we compare it with something that could be called critical values, and we stop as soon as at first time this inequality holds true. And on this type of procedures, I think last week talked Claudia Kirsch with different setup. So because this is a sequential thing, so the procedure is typically described by the stopping rule, and the stopping rule is says what I said here above, said as soon as this ratio is crossing this critical value C alpha, we stop, and said here is that we go for k from 1 up to m multiplied by capital T plus 1. So that means that we are going to stop at any case after these mt plus 1 observations. Okay, this is so-called closed-end procedure. There could be the situation where the T is infinite and said, but we are not going to talk about this. And what we want, that the requirement are on the constancy and this critical value side that if there is no change, so that means the null hypothesis holds true, that the probability that we stop is equal alpha, where alpha is a number between 0 and 1. So typically alpha is close to 0, so that means that this is the level of the test. But we can have a look going back to this, that this is somehow can be chosen, for example, 1/2, and then we have some kind of median behind it, but I am not going to work with it anymore. And then what we want, that if the alternative holds true, that we stop with probability 1, so that means the test is consistent. In both situations, we consider that m, that means the training sample or the historical sample, have the size tending to infinity. Okay, so this type of procedures were considered for the linear models in a number of papers. I will just mention here some of them. So probably one of the first papers in this area was written by Chu, Stigbombe, and White in '96. Then 2004, there was a paper just on the change, on the kind of sequential QSU methods. Then again, also another work was done by Zeilis, Gleich, Kreiber, and Hornig, 2005. And in fact, the motivation for the paper, for the results I am going to present, is coming from this paper, which is concerning the changes in CAPM models. But this is done for the functional data, and the procedure is based, I would call it, on L2 norms. That this is highly non-robust because it's known that generally that as soon as the data do not follow normal distribution, then using the least square estimators is somehow questionable, because that can be a quite effective by the outliers. Just saying, so that was the motivation. And otherwise, there are the other papers, just the names, yeah, Bombay Kirsch. And I had some times ago the PhD student who just treated the monitoring and using, instead of L2 norm, L1 norm, but independent observations. So this is connected with the story. Okay, said, but now the motivation, okay, there would be, so consider the robust procedure. It means that we just extend the L2 procedures to some, using, say, some other loss function, but here is a motivation going from the data set. We have a, okay, so what we have a daily closing prices of being in General Electric, and this is, here is the period. And then said that were the RTJ for this market for portfolio. It was used standard and 500 P per 500. Then we used for the data the sequential monitoring with least square estimators L2 and L1. And so the historical period was 400, and then but here should be 2001, not 2011. So here is another misprint, sorry for this. And so that goes, if we apply, I haven't spoke about the procedures, but just the picture. So we are doing kind of, we can just have a look at it as a possible procedure. So that if we use L2 or least square estimators for taking these two kind of assets, then it detects the change on 17th of September 2001, so that it's just close after the 11 September. So, but what we have here is just, yeah, this is L2. If we just have a look at it, so it immediately means that we are rejecting quite soon the null hypothesis, because of course these vertical lines are corresponding to various critical values, and said always we cross them. If we take L1 estimators, the situation is completely different. If you look that, you see this is the set comparing the black curves, that we see that it's below the critical value. If we just have a look on the blue, it's the same, and the red one, so this is corresponding to various weight boundary functions. We don't reject. The issue is that on one side we have that L2 method says there is a change, but these procedures don't say that there is no change. So there is a certain possibility to choose the Huber. I will mention it later on. This is Huber. This is something between L1 and L2, and so it's somehow, it shows that there is a change, but it's not such a big things as in before. So that was motivation, because we would get, using L1, L2, we got a different inference. That we said, okay, let us have a look on this, on some robust procedures. That if we say robust procedures in linear models, mostly the multivariate situation, you have the paper what I would mention by Wu 2007, robust estimators, dependent variables, Portnoy Conquer in 1990, multivariate but independent, and there are the papers by et al, multivariate and independent. And what is here the last thing are the somehow in Genton and Ronchetti 2008, there was a first robust procedure introduced to the CAPM models. That means no change point behind it, but just there is a somehow motivation for considering robust procedure. Is it? I think that one of the co-authors is sitting here. I think that this is. So that was somehow that we found out that someone tried to apply the robust procedures. That here is now it's coming to the situation that we have multivariate observations. That means that we have d-dimensional situation, d assets, and the formulation is as follows. These are these Rij, and here we have the coefficient alpha 0j, beta 0j are the value parameters before the change, and here is after the change. So here is a k star. So this is what we do not know. Of course, the problem is that we do not know k star. And here we use a transformation that we subtract here always the average of all IM set. And then the estimators could be defined, we will take based on the training sample, and how they are defined. Generally, we have rho j, this is a convex loss function with the derivative psi j. And so the solution, the estimators are defined as a minimizers of this sum of things. That we can, in fact, how we did it, that we consider for each component, we consider generally different loss function. So it's done component-wise. And then how we use it, we calculated M residuals. These M residuals are defined as a vector. Here is a psi1, and this is a usual residual, which is calculated as a difference where we have the observations minus the estimator of alpha j based on the training sample, and this is M estimator related to this psi. And we subtract, and still here is this is the RMI, this market portfolio, and here is the estimator set. We use set for the new for the starting, we use these estimators based on the training sample, and said how it looks like the test statistic. This is somehow the quadratic form. So this is the test statistic based on M plus k first observations. This is a quadratic form. Here is the sum of these, sum of the weighted M residuals. Here is this here also, but this is here what is in between is the estimator of the asymptotic variance of this term. Okay, we have to estimate it. So this is how it looks like. So this is a quadratic form, which is usually used for the multivariate situation. We need kind of standardization, and this is like that. So now the typical choices, because that's important, that what is usually considered, say, in the practice is, that means that what I call L2 procedure, so that means that rho x is x squared, and this psi x is equal x. So this is the classical situation. This is the L2 situation corresponds, in fact, the assumption that we have normally distributed observations. Then we have the L1 procedures, and this is based that we have the so that rho x is absolute value of x, and then psi function is only plus and minus 1. And the third one, and probably most often used, is so-called Huber function, which is somehow absolute value of, there shouldn't be the absolute value of x. Oh, sorry, there should be x only if the absolute value of x is smaller than equals some constant, and it's just constant k multiplied by sine x otherwise. So this is the most, this is somehow in between these two upper. So this is most often used. Then there are also, I will mention it later, that there are also the quantiles who were mentioned here last week also, and also somehow the score functions that are used generally in the likelihood ratio. Okay, so now shortly, so now assumptions that we have, assumptions will be on the psi function that can be quite arbitrary. Then on the dependence, the situations that I will just present shortly what we assume on these psi functions, that we assume that they are monotone. So that means this is related to the fact that we assume that this rho is a convex function. Then we take that lambda jt is an integral of the function psi and f, and we assume the following, that this is 0 at point when t is equal 0, and in the neighborhood of 0 there exists the derivative, which is somehow Lipschitz, so that there is some smoothness behind it, and we assume that the derivative at the point 0 is positive. So what is behind it, that the psi function needn't be really smooth, but if this is, say, like for the L1 procedure, we have sine, so that we need some smoothness around point 0. Okay, this is what is behind it, and then we need some some assumptions on the moments which are described here, so that we need the moment 2 plus delta, where delta is positive, and somehow kind of this type of relation. Okay, so this is what we need. So the next thing is the assumptions on the regressors, that I said that we are working with this LPM approximability, so that we assume that RMI this is a Bernoulli shift. In fact, we assume that this moment is finite, and this approximability via somehow the finitely dependent or L dependent random variables is here, so that it's behind it, that you can find somewhere closest sequence of the random variables that are M dependent. So this is one thing. Concerning the error terms, we need that, of course, something similar, that we have similar assumption for the error term, that there are the Bernoulli shift. But then we need the assumptions on the M approximability, not on the original on the original error terms, but psi epsilon a. So that means that if we take, say, L1 procedure, so this will be either plus or minus 1. And here we have similar assumption. Yeah, so there is psi only for the L2 we get just. Okay, this is. And so then here is the first result when we get the limit distribution, so that if we have this is the sigma is this long rank variance sigma, and this is the estimator. Here is missing the head. So if this holds true, so then max over k from 1 up to mt of the ratio, this is the test statistic, this quadratic form based on m plus k observations divided by the boundary function squared, so that it will converge to the supremum of the sum of squares of the independent Brownian motion as divided by t to 2 gamma. So this gamma is so this is corresponding to the situation when we have that the boundary function is of this type. It depends on gamma, and gamma is from the interval 0, 1/2, and it's open at point 1/2. So that in fact it's somehow done in the way that we get under the null hypothesis somehow, I would say, nice limit, in spite of the limit distribution on the random variable on the right hand side. It's known only for some very special situations. Typically we have to simulate it, but nevertheless we have the limit distribution, and it can be used for constructing the test. So this is already. So the question is how we perform the test. So we have to, for chosen alphas, which is a level of the test, we have to somehow find the critical value, or the 1 minus alpha quantile for this random variable, and then to use it as an approximation for this critical value. So that's easy. So here is, I would just say what is said. The proof follows similar issue as for the L2 situation, but we don't have the explicit expression for the estimator, so this is becoming everything much more complicated. So the first thing that we need some asymptotic representation of these M estimators, and we get that this is of this type. So we don't, so here is that this OPM to some minus eta. Okay, this is what is we need. Then what we need is that, in fact, this weighted partial sum of these M residuals behave in the same way asymptotically as this partial sum of, but here is psi epsilon I minus and this is coming from using the estimator from the training sample set. It's like that. And then we get, we have we create a process ZMT, and that can be already, because due to the assumptions we have there is that it converges to the Wiener process, to the Gaussian process, and here is the sigma is the covariant structure. So this is for the main thing. And then here is once more said that how we get the C alpha. It's chosen in this way. It's usually one thing said it's typically unknown. You can use it either simulating this random variable, or also the bootstrap can be applied. So now the next thing is, of course, so that we have at this moment the whole test procedure, but the question is how it looks like under the alternatives. That it's here only, it's simple local alternatives that we have here. Their delta M is just shifting the shift, but that means that we assume that delta M is tending to 0, but not too fast. We have here that if we multiply it by the root n, it's converging to infinity, and if the change, this beta J1 is non-zero for at least some J, some of the components, and the change point is of this type, so that we get that it's converging, converging in probability to infinity. So that means that we have from here the consistency. We proved, in fact, something more neat result that in the situation than when this delta M multiplied by root n is somehow non-zero, but not tending to infinity, so that you one get is something what can expect it. So that means that this procedure has these nice properties. And what is next? Said shortly said, I assume in the theorem that we have an estimator of the variance matrix sigma, which is somehow consistent estimator. So this is what we need to estimate. We can use the Bartlett type estimator. Okay, here we use this, in fact, this M residuals. They are, look here, so that's parallel to what we know for L2. And so if it's chosen as it describes, that the resulting estimator has the needed properties. Okay, so just for this part, somehow some comments that critical values computed from the simulated, this limit distribution. This is one thing. The otherwise, Monte Carlo, and then what we used also was to use the bootstrap based on the historical sample, which means that this is the situation when the null hypothesis holds true, and we need the critical value related to the null hypothesis. That this is okay, that we get the correct, asymptotically correct approximation. Yeah, and so here are a few pictures. So here are the results of the simulation study, and so what we have is capital T equal 10. This is for Huber function for L1 situation, and this would be set for alpha equal, so these are the critical values for the alpha equal 0.05, and if we just say this always MC means that we have a Monte Carlo simulation, and this means bootstrap. So that means if we go, so this is a asymptotic, theoretical asymptotic, but if we just use on the data, so it's a reasonable approximation. It's not always identical typically, but that's usually true generally, that for the bootstrap we get slightly small values. Okay, and this is done for the different type of dependency. I think that it's, yeah, so that it somehow gives reasonable result. This is only for the, okay, and here are the empirical levels, but it's also looks reasonable. Okay, so there were done quite extensive simulations, and somehow general inference could be made that the test based on L2 rejects null hypothesis too often. There are many false alarms. Test based on L2 is too conservative, and so the recommendation is to use the Huber function, just no theoretical resulted by just results of simulations. Yeah, and the critical values calculated through the bootstrap are also fine. Okay. So this is concerning this. So far, just I think that. Okay, so I will show the simulations, the application to the real data, and then I will make some comment and switch to the panel to the functional data set. The application which is chosen here is said we have in fact not assets but somehow the sector. This is a word consumer staple, word financials, word health, and as a more market portfolio is chosen this MSCI World Daily Index. The training period was from the 31 of December 2004 up to the end of November 2006. That means that the training sample has size 500, and the monitoring period was then started on the 1st of December, and so this capital T was chosen in such a way that it was up to this time, and that was done for the Huber function. And okay, so here is the this is connect. Yeah, so here is if we take just two of these sectors, financial and healthcare, so it appears that the change point is here. So that we see that it's somehow here below, and it starts to grow up very fast. I think that this is, if I am right, this is connected with this mortgage crisis that was in 2007. There was a crisis started. Wow, the terminology. Yeah. This is sad that's around it. Sad, but if we take only now the consumer staple plus financial set, again the same things that we see that after the date, which is somehow connected as a starting for the crisis, it goes upside. But if we take now the third pair, which is consumer staples and healthcare, what we see is something completely different pattern. So this is the date which was somehow counted as a starting point of the crisis. It doesn't go up, but it goes up to here somehow into the middle of the year 2008. So that means one can make the inference from here that the financial world reacted immediately, but concerning the consumer staples and healthcare, the change came much later. This is probably one can expect that. But that was done based on the Huber function. Okay, so just final remarks to this part. That the results were formulated for the CAPM approximability, but there can be, but I see another misprint here. But I had a student who did the same thing for the alpha mixing. Proofs are slightly different, but the final results are the same. Then concerning this robust approach offline, said what is probably relatively new, that was offline robust procedures for general regression models were studied by Chochola and Hushkova, and I think it's somewhere in the referring process at this moment. Further possibility. So this is, I don't know whether here is someone more from the robust statistics that I used here. What is it here somewhere? The chalk.
Yeah, other side.
That I had, say, d-dimensional situation, and I use that generally for each component. We have different function, loss function, and also then generally different score function. But if we take it as a d-dimensional set, more natural would be to choose some loss function and to put here, but it's a question, set some kind of norm of, and I would put here, say, for simplicity only this thing. So that means that there will be inside norm. Okay, this is of course possible. Here we had only just component-wise. That's possible. So everything could go through, but the issue is that already, if we start to, we need to say to switch from the minimizing some of these rho j's, that we need to switch to the, in fact, to derivative to get the equality to zero. So that becomes much more technical, and set for the not change point problem, independent observations that was done in 1990 but that was ZD and plus some others. So that was done, but this is much more technical. So probably that is better, more suitable theoretically choice, but it's so that we haven't done this. Okay, this is one thing said. That's one thing said. What else is here said, that as a psi function, we can choose also what is corresponding to beta quantile. So this is again kind of psi function that can be handled through the procedure, or there can be score function related to the ratio, to likelihood ratio. And there is something which is not here, and I remember now that what we had in our procedure was that we have this, that we estimate the alpha m and beta m based on training sample or historical data. Yeah, but if m is large, so then it's fine, because what we needed some asymptotic representation. If m is large, that's fine. But if m is not large, so then it's worthwhile to update the estimators, that instead of using this, using so he should be beta. Okay, so that can be done. But here one said this can be done, and of course here probably used for some recursive estimators. That can be done, but it's more complicated computationally. Theoretically, it's fine, because usually as soon as you have a as soon as you are before the change, that you are under the null hypothesis, so that's fine. But afterwards, of course, there can be the influence, the change, but we usually stop relatively early. So that can be done, that can be proved that we stop if we take in comparison here that we have m plus k star under the null hypothesis that what is the rest, there is only small part is somehow contaminated, I would say, the alternative set. That's usually, so it's convenient only as long as m is not large enough. So I think that this is connected with this part. So what we had was the model that we had D assets, so that was the D-dimensional, and that was, there were the parameters alpha, beta, and beta was somehow parameter of interest, not alpha. So next I said that I will mention something on the robust monitoring for the high frequency portfolio, or if we have the functional data. So what is that? This is the original formulation done by the paper I mentioned, that was Ale, Horvath, etc. So this is what we have additionally before that there is this S. As S is in the interval 0, 1, so that means that the observations are now always the random functions on the interval 0, 1, and then additionally we have, again, it's D-dimensional, so this is a D-dimensional, and it's like that. So we have here, yeah, this is what we had in before, how it proceeds. But you see, alpha, beta are D-dimensional unknown parameters. Again, just betas are the parameters of interest. So the issue is to extend the procedure that we had in before to this particular situation. So what we assume is the following, that we have the observations are, I hope that, okay, it's still, at first it's what we have the problem. This is what we had in before, that alpha and betas for the training sample or historical data are not changing. And the null hypothesis that we have the betas always the same, alternative is it changing at some point, m plus k star, so that's quite similar. We can rewrite the model in the way that is component-wise, and this is the null, the part for the null hypothesis, and this is a change for the parameters, and here we have the delta m, which is somehow the amount of the change. Okay, so now so that will go now parallelly what we did in before, but particularly so we define again these m residuals. At first we calculate here is S nu, because we don't calculate it in all points as from 0, 1, but only in some. We choose particularly this points, and then you see this is component-wise, that is what we had in before. Then we create a vector out of it, and we have this thing set. We have here additionally that is depending on the time S mu, yeah, that is a point in this interval 0, 1. And now how we create the statistic, so if we just look here, so this part, this is what we had in before, and what is new here, that we have here this point as nu, and we are making the average of them, so at nu from 1 up to n, and this is multiplied by 1 over n, so that means that what we have is interval 0, 1, it's divided, we choose it equal intervals, and each, yeah, so we in each point we calculate these things, we sum it over nu and multiply, so we take the average. Then of course what we have here is again this estimator of these long range variance, and this is done. So this is somehow the change in before, again, because it's this is a quadratic type of statistic, we will assume that we want that the test statistic will be similar. Okay, what is said here is something more on the estimator, but it's because we have here the interval from 0, 1. And the test statistic is that similar what we had in before, just this Q hat and KM is a different, has a slightly different case. So what is the aim to get the same result now as we had in before, but we have the situation with the high dimensional data. So here are the assumptions. So I will just go through it very shortly. The first thing is just connected. Yeah, here is what is in fact similar to what we had in before. So that we have again the Bernoulli shift, but here we have the process. And what we assume that the third moment of this RMI is finite, but the supremum over all s from the interval 0, 1 are finite. Similar assumptions on these error terms, but here is now the assumptions of the finiteness of the moment, and these two sequences are independent. So this is somehow quite similar. In the next page is somehow also similar to what we had in before, but said because we have here this S set, we take this is what we had in the before for the just a multivariate situation for fixed S. But we have here supremum over of the interval 0, 1. Similar is the assumption concerning the psi EI. So here we have supremum. If one would just, if we would want, we could just somehow slightly relax it, but on account of much more complex proofs. So, but what is here new is, this is now concerning these points when we have the observations. So the first thing is that the number of, and so this is the number of intervals, has to go to infinity together with m. We assume particularly that this is of this time, and if we just said what we need is, this is kind of, the oscillations are not too large. So here you see just one, okay, so just to remind that this is the piece moment to the power of 1 minus p. And so here is that, in fact, we have for fixed Sj, we have that this is somehow small. We take the supremum over all h from the interval 0, 1 over n, and we take the average of it, and here is log m. If we would slightly strengthen the assumptions on the moments of r or psi I, so that we could just forget it. So this is what we need for the kind of oscillation. So that's different from what is, you have to be here more careful because this psi function can be this, say for this sign, that can be plus or minus 1, so one has to be really very careful with this assumption. Okay, so we have these assumptions, and so the results are then the same set. I am not going to repeat it, but just show the application. This is, I think that it was from the originally for L2 done in that paper by Aue et al. Said there were the sectors: Boeing, Bank of America, Microsoft, AT&T, ExxonMobil. Market portfolio was this Standard and Poor, and said the intraday behavior of the process is defined at time S as a difference between log prices of the stocks at time S and S plus 15 minutes. Yeah, so this is how it was done. So this is these market market-related processes defined analogously, and that the historical period was from the January 29th of 2001 and consists of 120 trading days. And this is the period for where the parameters were quite stable, so that was tested based on these 120 days. And then the monitoring horizon, so that this capital T behind it was chosen 360 days, and it corresponds to capital T equals 3. And it covers, of course, and it's behind it, this is this September 11. Okay, so here I will just show the pictures. And here are the L2 estimates of the portfolio based on the moving windows of 10 observation set in order to get the picture how it looks like. So I think that what is here is what is here is related to the September 11. This is when it was not already influenced by the observations before this 11 September, and this is just, this is corresponding to the September 11. And then what is probably not almost seen there is just then the change was detected. So this something which is gray and one can hardly see it. So that's here. Okay, so that was quite early, but that was done just to have a picture of what's to have said. Not much can be seen, at least I don't see too much behind it. So then the next thing is the following. We take altogether all five sectors, all five companies, and what is here is that the lower part, this is related on the, this is related to the Huber and L1. It's almost not seen, but this is corresponding to the L2 norms. That what we see here, if we put everything together, that you see there is of course the change detected almost immediately. L2 norms is leading to such a jump. And then if we take this just as exons, that we have that it's not, there is a difference, but it's not such a big difference between two. It's rejected, but it's somehow the curve is close. That if we take, but what is BA? So I will just, BA is Boeing, sorry. If we take Boeing, so there is a really, we see that here is a peak from L2, so it's immediately rejected. But if you have a look on the L1, and there is behind it also the Huber, so we see that it's somehow slightly crossed the critical value, which is over here, but it's staying here, and it starts to growing afterwards. So this is somehow different behavior. If we just look at the last picture, we see that there is no influence, that it stays behind, because at the point 1 there is a critical value. So here is the main issue is this Boeing issue, and so what then we did was the following thing, just naively. At first we omit the first 5 days after September 11, and then 10 days excluded. So that if we just have a look here, that this what it has a peak here is related to the L2 norms, and then this is corresponding to Huber. So it's almost, and there is behind it still L1 side. We see that it's like that, and it's starting to grow much later. And the last picture is that there was 10 days excluded, and said what we see that only the L2 norm is going slightly above the critical value, otherwise it stays there, and the change is indicated much later. So that was sometimes, I think, in May next year. So what one can infer from this, that you can see that there was, of course, after the September 11, there was a shock, but that was not permanent change. It went up and then it went down, so that was kind of outlier. So the L2 norm somehow classified as a change in the model, while the L2 and Huber are somehow not so much influenced. It's slightly above the critical value, but it's really slightly. But assuming so, there was, of course, the influence of this shock, but if we omit the 5 or 10 days, that we see that the situation is different, and the change then occurred somehow much later. Yes, that was somehow, this is saying that using all these L2 procedures, one should be much more careful with it, and eventually use some other, say, procedure to check whether this is really a change or whether this is an outlier. In fact, in the paper with the L2 norms that was done, how it was done, so I think that there was somehow taken just, it stops after rejecting, and then there were, I think, 2 months is left, and after that the procedure was applied, and again to show what is here, that the change was at approximately the same time as it's shown here. Okay, so this is probably all what I wanted to say. So this is just say, be careful with using all these L2 procedures, because this is related to the normal distribution. It's not saying not to use it, but be very careful, because you see it appears in this situation that the L2 norm or these type of procedures are very much influenced by the outliers. That's all. Thank you for the attention.
Questions or comments?
Maybe 2 questions or remarks. With regard to this question of update, when M is small and you update, I'd like to point out that Moshe Pollack and I considered that problem around 1990. I don't remember the publication because we did it once and gave up as a very hard problem. But the question we tried to ask is, how large does M plus K star have to be so that you don't lose anything compared to having a guaranteed?
Yeah, so I agree with you. It's a very difficult problem. So this is why I mention it here only like that, not mention it, because it's really hard problem. I had a student who tried to do something with a very simple model.
We considered only a very simple model, and then we tried to compute how much more it cost you in expected delay.
Yeah.
If M plus K star was relatively small.
Yeah.
And you actually do quite well, but when you start pushing the boundary, it gets to be a hard problem. The other remark I would like to make is that we've had many arguments with laboratory scientists about trusting a single observation that indicates a change point. And at least in some contexts, their point of view is that if you're dealing with an experimental science, there's a way to go into the laboratory and check to see whether you have an outlier or some real information. And they can be very reluctant to give up even one observation that looks as if it's an aberrant observation. Although we as statisticians think that if you see something stable and then a big jump, then it's more likely to be an outlier. So here where you don't have this option to reperform the experiment,
Yeah.
I think a different attitude is definitely appropriate from the case
Yeah.
where there's an independent way of taking another look to see if what you observed is an outlier or not.
Yeah, I agree with you. Yeah, said I don't have experience with any labs. Was just, you see, I'm from Prague, and said somehow my colleague and I worked for a long time in robust procedures. That was somehow, yeah, and I think that it's somehow
Well,
shown.
it's the difference of dealing with experimental and observational data. With observational data, you don't have
Yeah,
this extra set of options. You have to protect yourself against
yeah,
making this kind of mistake.
In your simulation part 1, you compared 3 procedures. And I just wonder whether you adjust the level of the 3 procedures or choose the critical value based on your asymptotic results.
Don't ask me by heart. I haven't done simulations, but I think that was somehow adjusted because that is what we found out from other situations that has to be somehow adjusted. Yeah. But only in simulations, but I haven't done simulations, someone else did it. Yeah, but it must be done, otherwise you can, one has to be very careful, yeah.
And also, how hard to extend your procedure to test the change in both alpha and beta? Because in the beginning, you put up this CAPM model. If you trust that, then the change of beta will drive the change in alpha as well in your setup.
Yeah, but you see, going through the proof, you can do it for the change in the both, but this was somehow simple procedure. But if I understood well in econometrics, mostly betas are of an interest. But you can, concerning the proof, you can extend it.
But then they will take away this discovery rate. Because in your setup, you start with this.
But
then you change it. Once beta changes, in your
but that means that this alpha is also changing. But so somehow there is something behind it that the procedure is done like that. That as soon as there is only change in alpha, not in beta, so that will not be, the procedure will not reject. Okay, this is somehow there is behind it some.
I'd like a clarification since I don't understand the subtleties of it, or maybe even anything about the CAPM model. So let me just ask it about simple regression. And that is, a change in beta, you accumulate information very quickly when there's a change in beta. When there's a change only in alpha, you accumulate information more or less at the rate of n observations for n units of information. But with a change in beta, you accumulate n squared units of information.
But it very much depends on so here it would be on this RIM, it very much depends on it, how, so that shouldn't be set in the.
Well, I would think that complicates when the situation with both parameters change, but now when you take local alternatives, you sort of scale out that difference in such a way that it doesn't really affect you. So I'm not sure what it all means.
What I would say, theoretically, one can construct the statistic for the change either only in alpha or change in both. That is theoretically possible. So there is not a problem. I am not such an expert in the CAPM model because I know that there is, if I understood well, there is a discussion always going on whether this is the model is appropriate or not. There are many variations, so that I choose one of the, we choose one of the versions.
Maybe a comment about the paper with Helvetia Ronchetti. The idea there was to look at robust prediction of betas. So if you're just interested in estimating beta, you can use robust procedure, and if you have outliers. But if you want to predict the future, then you need to do some shrinkage of the robust beta towards the non-robust least square estimator. because there's a bias variance trade-off, and you can reduce the bias by doing so. In your case, if you fit for a certain period of time, and you look at prediction in the future, either before or after the possible change point, it seems that there is such a situation where you should maybe do some kind of shrinkage. You're not considering this.
No, we haven't considered. No, only what I presented here. No,
It
nothing.
seems that it
Yeah.
with the same.
Yeah,
setting.
that should not. Yeah, sad. I think that should go, but I can't tell you now. Yeah, by heart how it would be.
Well, if there aren't any other questions, let's thank you again.
Thank you.